Welcome, data engineers and machine learning practitioners. Let's get started on mastering the implementation of Spark ML pipelines for large-scale inference. Welcome. Today, we are tackling a massive challenge in modern AI, implementing Spark ML pipelines for large-scale inference. Let's start with the what. A Spark ML pipeline is a high-level API built on top of data frames that allows you to construct practical machine learning workflows. The basics revolve around chaining multiple stages together, such as text tokenization, feature scaling, and final model scoring into one unified pipeline. Why is this critical? Because in production, you must guarantee that the exact same feature engineering logic used to train your model is applied to your live inference data. If you miss a scaling step, your predictions are useless. How do we do this? We assemble these stages into a pipeline object. Taking a deep dive, when you use this unified API, Spark treats the entire workflow as a single directed acyclic graph, or DG. This means Spark's Catalyst Optimizer can peek under the hood and optimize the entire execution plan, making your inference runs incredibly fast and efficient across terabytes of data. Take a look at this flowchart illustrating a standard Spark ML pipeline. Data flows from left to right. Raw data enters the pipeline and passes through feature engineering stages here, a text tokenizer, and a feature scaler. Finally, it hits the ML model to produce predictions. The gray box represents the pipeline itself, encapsulating all these steps. By keeping everything in this box, Spark ensures no steps are skipped when new data arrives for inference. To build these pipelines, you must master its two core components, transformers and estimators. What are they? They are the fundamental building blocks of Spark ML. Let's cover the basics. A transformer is an algorithm that takes a data frame, appends new columns, and outputs a new data frame. An estimator, on the other hand, is a learning algorithm. It must observe data to learn parameters like a logistic regression model finding its weights. Why this separation? It cleanly isolates the phase of learning from the phase of applying. How do you use them? You call .fit on an estimator to learn the data, and you call .transform on a transformer to make predictions. Here is the deep dive. An entire pipeline is actually an estimator. When you call .fit on your training data, the pipeline learns all necessary parameters and converts itself into a pipeline model. For large-scale inference, we only care about this pipeline model because it acts purely as a giant transformer. This diagram breaks down the relationship between estimators and transformers. On the top path, you pass a training data frame into an estimator using the fit method. This learning process produces a transformer, which is your actual trained model. Now, look at the bottom path. When we move to large-scale inference, we completely ignore the estimator. We pass our new, unseen inference data frame directly into the transformer using the transform method, which yields our final scored data frame. You might ask, why use Apache Spark for large-scale inference instead of traditional tools? What it comes down to is Spark's distributed architecture. The basics are simple. Spark divides your massive datasets into smaller, logical chunks called partitions and distributes them across a cluster of worker nodes. Why is this necessary? Because if you try to run inference on a billion rows using a single node tool like Pandas or scikit-learn, your machine will run out of RAM and crash. How does Spark solve this? Spark pushes the pipeline model directly to the executor nodes. It brings the computation to the data, evaluating partitions in parallel. For our deep dive, you should know that Spark data frames utilize the Tungsten execution engine. Tungsten manages memory off heap, meaning it bypasses traditional Java garbage collection. This allows Spark to score millions of rows per second with bare metal performance, making it the ultimate tool for big data inference. This cluster architecture diagram illustrates the sheer power of Spark. At the top, the driver node broadcasts your trained ML model out to executors 1, 2, and 3. Simultaneously, massive chunks of data partitions 1, 2, and 3 are fed directly into these executors. Each executor works independently, applying the model to its local partition. The result is true parallel processing, allowing you to generate predictions at a scale impossible for a single computer. Let's get practical and construct the actual inference pipeline. What does this involve? It is the code you write to load a previously saved model and score incoming batch or streaming data. The basics require you to use the pipeline model.load command, pointing it to your model's location in cloud storage like AWS S3 or HDFS. Why do we do this? Decoupling the training phase from the inference phase allows data engineers to run scheduled, highly reliable scoring jobs without retraining the model every time. How is it executed? You simply read your incoming data into a Spark data frame and call model.transform, df. The deep dive here is crucial. Spark uses lazy evaluation. When you call .transform, Spark does not immediately calculate the predictions. It merely updates the catalyst logical plan. The actual heavy lifting only triggers when you invoke an action, such as writing those predictions back to a delta or parquet table. Let's walk through the sequence of events in your code. First, your Spark app requests the saved model from cloud storage using the load command. Next, you call transform on your new data. Notice how the Spark engine responds. It only updates the logical plan because of lazy evaluation. It's not until your code explicitly calls an action, in this case, writing to Parquet, that the Spark engine spins up the cluster, physically executes the distributed inference, and writes the predictions back to storage. To be a senior expert, you must know how to optimize your inference performance. What does optimization mean here? It means tuning your cluster resources and data layout to maximize scoring throughput. The most important basic rule is managing partitions. You must ensure your data frame partitions roughly equal a multiple of your total executor cores. Why? Because if you have data skew where one partition holds 80% of your data, most of your CPUs will sit idle while one core struggles to score everything, destroying performance. How do we fix this? Use the .repartition method to evenly balance your data across the cluster before calling .transform. Now for a massive deep dive tip. If your ML pipeline requires joining reference data during feature engineering like mapping zip codes to regions, force Spark to use a broadcast hash join. This sends the small lookup table to every node, completely eliminating network shuffles, which are the enemy of Spark performance. This decision tree is your optimization checklist. When incoming inference data arrives, ask, is the data skewed? If yes, you actively repartition it to utilize all cluster cores. Then, you apply the pipeline transform. Next, ask, does my pipeline require joining a lookup table? If yes, you must wrap that table in a broadcast variable. Following this path guarantees an optimized, shuffle-free output, saving massive amounts of compute time. Sometimes, the best model for the job isn't built in Spark mlib, it's a scikit-learn, XGBoost, or PyTorch model. How do we run these at large scale? We use advanced pandas UDFs backed by Apache Arrow. The basics involve wrapping your standard Python model inside a Spark user-defined function, or UDF. Why is this advanced? Because historically, passing data from Spark's Java virtual machine to a Python process happened row by row, which is incredibly slow. To fix this, we enable Apache Arrow in the Spark config and use the @pandas UDF decorator. For the deep dive, Apache Arrow is an in-memory columnar format. It allows Spark to transfer entire batches of data from the JVM to the Python worker process with zero copy overhead. Your Python model scores the whole pandas series at once. This vectorized execution speeds up inference by 10 to 100 times compared to standard UDFs. Look at the data flow in this diagram. Instead of a slow, row-by-row bottleneck between Java and Python, the Spark JVM memory packages thousands of records into an Apache Arrow batch. This batch uses zero-copy transfer to instantly appear in the Python worker's memory. The non-Spark model performs vectorized scoring on the entire batch at once and fires it right back to the JVM. It is the ultimate bridge between big data and deep learning. Let's cement this with a real-time, highly important use case, telecom churn prediction. Imagine a major telecommunications company that needs to identify which customers are likely to cancel their service, and they need this list every morning. The challenge is immense. They generate millions of call detail records and billing logs daily. To solve this, we build a Spark inference job. We load a pre-trained pipeline model that contains all the complex string indexers, vector assemblers, and a random forest classifier. We read the massive daily data drop from an S3 bucket, call .transform, and immediately filter the results for a churn probability greater than 80%. The result, Spark's distributed processing scores 50 million users in a matter of minutes. The output is appended to a high-speed marketing database, allowing the retention team to send targeted discounts before the customer ever picks up the phone to cancel. This architectural flow shows the end-to-end churn prediction pipeline. We start at the top with daily telecom logs sitting in S3. Spark reads these rapidly as a Parquet data frame. We introduce the preloaded churn pipeline model, which transforms the data into a scored data frame. We apply a filter to isolate high-risk customers and write that highly valuable subset directly into the marketing database for immediate business action. Let's summarize our journey and review best practices. We learned that Spark ML pipelines are critical because they unify feature engineering and model scoring, guaranteeing consistency in production. To optimize, you must tune your partitions to your cluster cores and eliminate network shuffles by broadcasting small lookup tables. If you are using deep learning or scikit-learn, always leverage Apache Arrow to vectorize the data transfer. In production, be proactive, constantly monitor the Spark UI and directed acyclic graphs to spot and fix bottlenecks. Finally, ensure you save your precious inference outputs to optimized columnar formats like Parquet, Delta, or Iceberg. I hope you found this deeply educational. To take your data engineering skills to the ultimate level, please invite learners to like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. See you in the next session. Our final diagram is a simple mental checklist for you. Follow the best practices, strictly use the pipeline API to prevent data mismatch, aggressively tune your partitions, and embrace Apache Arrow for external models. Do these 3 things and you will effortlessly scale your machine learning inference to handle any volume of data the world throws at you.